So today we're going to continue the maximum likelihood estimation of the spatial model. So on Monday we saw the lag model, and the main takeaway points from that is that it's complicated. So you have to set up the likelihood function. This is a non-standard case. The asymptotics are not standard. The laws of large numbers and central limit theorems are not standard. There's actually two different ways to go to the limit, and it matters. It's not like this is just a mathematical thing. And then we saw that the computational aspects of it are actually quite complex because they involve the evaluation of determinants and inverses of matrices of the dimension of the data set, which is n by n, so that doesn't scale that well. What I want to do today is basically do the same thing for the error model, and it's the same general idea. So you get the likelihood function, you find the first order conditions to find the estimates, second order conditions to construct an asymptotic variance matrix. And then we'll talk a little bit about concepts of predicted values and residuals, which is not as straightforward as it is in a standard regression. And depending on time, because I do want to spend some time today on walking you through maximum likelihood estimation in GeoDa, and if we have time in GeoDa Space as well. Of the two, the one in GeoDa is the better one. GeoDa Space is maximum likelihood is in there mostly for pedagogic purposes, but it's not very efficient. It doesn't scale very well, whereas the one in GeoDa does scale very well. I'll talk about that more. So I don't know how much of this material I'm going to cover. I also have some discussion of model comparisons. How do you compare the fit of these models? There, the takeaway is R square is no good, so you need something else. And then maybe just a few items of these computational issues. The readings are the usual. The technical discussion is in the Anselin and Ray book. And then the gory details of the derivations with the matrix partial derivatives and all that fun stuff are in the book, and to some extent in the chapter, review chapter. The Magnus paper is pretty much, it's a classic paper in Journal of Econometrics that lays out general approaches to estimate error variance covariance matrices that are a function of other parameters. So the spatial case is a special case of that, but this approach has been used in a lot of other cases as well, such as variance components, multi-level models, things of that nature. And lucky for me, I discovered this just as I was working on my dissertation, which, so I had done it the hard way, actually working out the derivations, but then this is an alternative way that couches it in a much more general framework. So if you're interested in the mathematical details, this is a pretty interesting paper. And then the paper by Roger Bevant and others is deals with more of the computational aspects. As we already know, a key component of this likelihood function is the Jacobian of the transformation, because we start with the error term and we don't observe the error term, so we need a model for the dependent variable for the y, which involves a transformation. And that Jacobian is this n by n matrix that we need to compute the determinant for. So there are a lot of different ways to do that. Maybe I'll talk a little bit about that if I have time. I'll keep an eye on the time so that we have I have a chance to show you the software. Okay, first I want to cover something that I forgot to cover last Monday, is the notion of predicted values and residuals. And this is often a source of confusion when you do this the first time. And the software doesn't make it any easier in some sense, because it gives you different options, different concepts of predicted values and different concepts of residuals. The first thing going back to the lag model, the first thing to note is that the traditional approach, which spells out the conditional expectation of your dependent variable, conditional on your explanatory variables, is not the form of the equation, which is rho wy plus x beta, right? Why not? Because y is in there. So you can't have a prediction for y if you need the value for y on the right-hand side. That doesn't work. Even though mathematically that's how you write the initial specification, as an expression for the conditional mean, the conditional expectation, it's not useful. So what we need to do is we need to get rid of this wy on the right-hand side. So instead we use this concept of the reduced form that we saw last week for the lag model. And so then if we take the conditional expectation, the conditional mean of the dependent variable conditional on the explanatory variables, it's a much more complicated expression. And you know, what we don't like is that it involves an inverse of this n by n matrix, which is, you know, a bear to deal with. Now, as it turns out, and you may remember this from my discussion of the spatial multiplier, if the weights matrix is rho standardized, and since rho is typically less than 1, you can write this inverse as an expansion. Identity matrix plus rho w plus rho square w square plus rho third power, and so on. So you keep going, and then it's actually computationally feasible to work this out, because rather than inverting this full matrix, you go to the expansion. And the expansion, because you're powering a number that is less than 1, the expansion fairly quickly goes to 0 or becomes negligible with some degree of precision. So if you have, you know, 0.5 and you have 0.5 to the 20th power, if you have a calculator, you see that's a very small number. And so you don't have to actually do the full inverse. You can do the expansion. And each of these expansions, if you look at this carefully, so the first one is I times x beta. That's easy. The second one is rho wx beta. But wx is a spatial lag of x, which we can do computationally really fast. And then the next one is rho squared wx. So that's the spatial lag of the spatial lag. So you can actually do this fairly efficiently without having to invert this big matrix. And that's how we do this in practice. So in practice, we then come up with this notion of a predicted value, which is from the reduced form. And that's how you have to do this, for example, in a system of simultaneous equations as well. When you have endogenous and exogenous variables, you want all the endogenous variables on the left-hand side. Otherwise, you can't solve the system. So this is something to keep in mind, because it's very tempting to use the top expression as the predicted value. Plug in the estimate for rho, plug in the estimate for beta, and all seems fine, except where does the y come from? The y is what we're trying to predict. So that's why we need to go with the reduced form in the lag model. Then the other notion is a notion of residual. And the residual, as we know it, is the difference between observed and predicted. But what is predicted? I've just argued that the best prediction is from the reduced form. So then the notion of a quote-unquote residual would be the prediction error, the difference between the observed dependent variable and the prediction from the reduced form, right? That's the bottom expression. However, as it turns out, in the test statistics, because you can treat rho and x as known, and because it is the difference between y and x beta, so you don't actually, you're not predicting y, you know what y is. In contrast to getting the predicted value, you don't know what y is. So for the residual, you can actually use the quote-unquote naive expression. And in fact, this is the one that's used in test statistics and so on that we'll deal with next week. So important, there's all, you know, kind of like a bifurcation, 4 different notions, 2 different notions of predicted value, one that doesn't make a lot of sense but can be computed, and another one that is a predicted value from the reduced form. And 2 notions of residuals, one which is a theoretical, the basis for the theoretical derivations of the diagnostics, and another one which is a notion of prediction error. How well does my model do in predicting the pattern for the dependent variable? Remember the difference between simultaneous and conditional models. In simultaneous models, we predict the full pattern for the dependent variable. So that was the lag. Now move on to error model. And the problem is we have different specifications for the error term. The one that I'll focus on is the autoregressive one because it's the easiest one. And why is it easy? Because the variance, and we saw this last week, the variance of the autoregressive error term is this monster there, scaled by sigma squared if we have homoscedasticity. And then we have the inverse of a product of a transpose of a matrix with the matrix, and that's our, you know, the same expression as in our Jacobian. It's the same big matrix, right? So the variance is the inverse of this. And we may remember from generalized least squares, we need the inverse of the variance. And as I mentioned last week, the inverse of this inverse is no inverse anymore. So we're in business. In contrast to, say, the moving average model that we saw last week, where the variance doesn't have an inverse, but then the inverse of the variance is a real inverse of an n by n matrix. So that becomes very difficult to handle for large data sets. And similarly, if we have other expressions for the spatial covariance of the error terms, say direct representation, which is a function of distance, a distance decay function, there again, we're going to have to take the inverse of this big n by n matrix. That's why, you know, we focus on this one. This is the easiest one. It's also one that reflects the strongest kind of spatial dependence, as we saw in the earlier discussion. So one way to look at it is that this is all about the error terms. So we don't really care about the significance of this parameter. And in that view of the world, lambda is seen as what is called a nuisance parameter. So it's a pain. It's in there, but it doesn't really matter in and of itself. Where it matters is to get a better estimate of the slopes, of the betas. If you remember my little simulation, if we ignore the spatial correlation in the error term and we crank up the parameter, we saw this, the distribution of the estimate stays centered on the true value, but it gets flatter and flatter, which means that the true variance is much larger than the variance that we think that OLS gives us, for example. So that's where the correction comes in. We need to correct that variance. And so in one approach, since the estimation problem is really a problem of efficiency, there are a number of estimation methods that we'll cover 2 weeks from now that don't even worry about inference for lambda. All they care about is to have a consistent estimate for lambda. And so that's a nuisance parameter perspective. And so then the upshot of this, and most of you should know this, is a special case of feasible generalized least squares estimation, and I call it spatially weighted least squares. So let's look at this a little more carefully. So the standard expression is, instead of x prime x inverse x prime y, we stick the inverse of the error variance covariance matrix in there. So of course we have to know what this is. In the textbook approach in GLS, it's taken as known. In practice, it's not. You have to estimate it, right? And we posited a specification for the spatial process that generates the error terms. And from that spatial process follows a variance-covariance matrix. We saw that a couple of weeks ago, right? That's very important. So the process that we posit is an autoregressive process, and we just saw the form of the variance. So the inverse of that variance, we can forget about the sigma square because they cancel out, is I minus lambda w prime I minus lambda w. So this middle part is the inverse of the variance. So we see it on both sides. And then one way to think about this is, what if we knew lambda? We could construct a new variable, which is called a spatially filtered variable, in that you take the original variable and you subtract the spatial lag, which is the average of the neighboring values, scaled by this parameter lambda. That's called a spatial filter. So if we make a spatial filter for x and we make a spatial filter for y, then spatially weighted least squares is nothing but ordinary least squares applied to these spatially filtered variables. Of course, the key point here is we need to have an estimate for lambda, and how do we get that, right? In parallel, somewhat parallel with time series approach, this is called a spatial Cochrane-Orcutt method. Okay, Cochrane-Orcutt method also creates a filtered variable, but then in time series, right? Is the variable at t minus the coefficient times the variable at t minus 1. This is similar in spirit, but as we saw when we talked about spatially lagged variables, it's actually different because we don't have the shift in time. We need to use this notion of a spatial lag, wx or wy, right? So with lambda in hand, we're in business. The question is, how do we get lambda? Unlike what is the case in time series, we cannot get lambda as a straightforward second step least squares regression. And we have to go full bear. So we have to do a full parametric specification. We have to assume normality for the error terms. That normality for the error terms yields normality for the dependent variable, which is the one we can observe. And then we can spell out the likelihood function and obtain an estimate for lambda from that likelihood function. So unlike the time series case, there's no shortcut. You have to do everything. And with lambda in hand, then we plug it into the feasible generalized least squares or the spatially weighted least squares, and we're in business. And everything else is the same as in least squares. The variance, covariance matrix, all that stuff is the same. So how do we get this log likelihood function? We again start with a multivariate normal distribution. Again, we cannot simply make the product of the marginals because they're dependent, so we have to deal with the full joint distribution. We again have this Jacobian, so this should all look very familiar, except that we don't have y minus rho w, y minus x beta, but we have the spatially filtered residuals. So the lambda comes in the spatial filtering of the residuals. Other than that, this is the same kind of approach as we did for the lag model. So it's the same general idea, but the likelihood function is slightly different. And as before, you cannot solve this analytically. You have to actually optimize this function. This is an optimization problem. And we saw that for the lag model, by using this concept of a concentrated likelihood function, we could reduce the problem to one of optimizing over one parameter, which is relatively easy to do, especially since it's well behaved, it's nice and convex. And so we're going to try to do the same here. It's a little trickier, and there are a number of different ways to approach this. But the first thing that we already know this is that the solution for beta is the feasible generalized least square solution. So that's basically OLS applied to the spatial filters. So conditional upon lambda, assuming we know lambda, we can get beta, no sweat. Assuming we know lambda, we can get sigma squared, no problem, right? So then, how do we get lambda? Well, these conditions are the first order partial derivatives that we said equal to 0. The result for lambda is this kind of thing at the bottom. And so this is a, matrix calculus person's delight, right? It's the trace of the partial derivative of an inverse of a matrix, and then that inverse of the matrix is in there twice, and that inverse has the lambda parameter, right? So this is a lot of fun. So basically, we don't go there. So we cheat. So this just tells you a little bit of, if you're interested, what these derivatives look like. So a lot of big W's, a lot of inverses, a lot of trouble, right? Now, instead, we can go the same route as before and use this idea of a concentrated log likelihood function. So instead of having beta in there, in that likelihood function, we replace beta by its solution. Its solution is the spatially weighted least square, so it has lambda in there, but that's okay. And same for sigma squared. We replace it by its expression, which also has lambda in there, but that's fine. So then the end result is a monster as a function of lambda. And it's a function of lambda through these different lagged y's and lagged x's, which are in there, as well as, of course, our friend the Jacobian. But this is a nonlinear function only in lambda, fairly straightforward to optimize. You get your lambda, you plug it into spatially weighted least squares, you have beta, you plug it in the expression for sigma squared, you have that, and then you have your variance covariance matrix and all that. Except, and this is where you can stop if all you care about is beta. But since this is a course about spatial regression, we're also a little bit interested in lambda, right? So how do we carry out inference for lambda? I mentioned the notion of an asymptotic t-test the other day. To do the asymptotic t-test, we need an asymptotic variance. And the asymptotic variance looks like this. And again, there's some monsters in there that we really don't like, namely the product of W with I minus lambda W inverse. This requires the inverse of an n by n matrix. So several pieces of software out there that do maximum likelihood for these models don't bother with this, because the optimization part is easy, the spatially weighted least squares part is easy, all these scale very nicely, except this does not scale very well because you have to compute this inverse. So one approach you could take is, well, I don't really care, there's other ways of doing inference, as we'll see next week. For example, a likelihood ratio test. So instead of doing an asymptotic t-test, I'm just going to do a likelihood ratio test, which is relatively straightforward to compute. So when you look at software, for example, in R, the routines to estimate these models by maximum likelihood, in some cases, do not bother with the asymptotic variance matrix because it's too complicated. It doesn't scale well. So the one thing that I wanted to point out, which is different from what we saw before, is that in the error model, the structure of the asymptotic variance matrix does conform to the standard case. So as we saw, if you remember, in the lag model, it did not, and that was part of the complication. So we had this block for the betas, and then the block for the error parameters, but there wasn't zero in the corners. So it wasn't block diagonal. In other words, there was a connection between the precision of rho and the precision of the betas, and there was a connection between the precision of sigma square and the precision of rho, which is very weird. You don't see that in a standard model. Here, there's a clear separation between the precision of the betas and the precision of sigma squared and lambda. So if, in fact, we don't care about the precision of lambda, that's fine, because unlike the lag case, the precision of lambda does not affect the precision of the betas. And we know, or maybe we don't, but just believe me then, that for feasible generalized least squares, all you need is a consistent estimate for the nuisance parameter. So as long as you can establish that it's consistent, you're in business. It doesn't have to be efficient, because at the end of the day, the efficiency doesn't matter because of the block diagonality, right? Now, of course, if we're interested in carrying out an asymptotic t-test on the spatial parameter, then we need the asymptotic variance matrix. And the standard error will give us a measure of the precision. Okay. Going back to these other two notions, the notion of predicted value and the notion of residual. First, the predicted values. Unlike the lag model, we don't have a problem. Okay? This is just fine. The conditional expectation of y given beta is x beta. Why is that? Because the mean of the error term is 0. It disappears. On average, it disappears. So that's just a classic case. However, there is an effect of taking into account the variance structure for prediction purposes, but it doesn't work on the unbiased part. It works on the precision part. And there's a very famous paper by Goldberger in long time ago on the notion of a best linear unbiased predictor, which takes into account, through the second term, the structure of the error variance covariance matrix. So the sigma inverse is the variance covariance matrix, and the C part is the covariance between the observed data and the new data. And this idea of the best linear unbiased predictor underlies the notion of kriging, the rationale for kriging, which is the spatial prediction I mentioned the other day when I talked about the conditional perspective. So you might see this in the literature every once in a while. It's a very general kind of finding that applies not just to the spatial case, but to any case, to the time series case, and so on. Then the residuals are often a cause of confusion, because the standard residual is a difference between observed and predicted. And as we just saw, the predicted doesn't have anything spatial in it. So these residuals, if you map them or if you do some diagnostics on them, will look like they are spatially correlated. And they are, because we haven't taken out the spatial correlation. So if you want to see the clean residuals, or you want to see, in other words, the effect of correcting for spatial autocorrelation on the residuals, you have to construct the spatially filtered residuals. And so those are the spatially filtered dependent variable minus the spatially filtered predicted values, so to speak, using the estimates for lambda and beta in that expression. So oftentimes people come to me and they say, you know, I did this in GeoDa and I mapped the residuals and they still look highly correlated. Yes, they are. It's only after you take out the correlation with the filtering that they should be more or less random. Right? So this is, again, something non-standard. So in each of these models, we have something non-standard. In the lag model, it's the predicted value that's non-standard. So the predicted value in the lag model should really be based on the reduced form. In the error model is the notion of a residual that is non-standard. And if you want residuals that are not spatially correlated, you have to construct the spatially filtered residuals. Okay, I'm going to skip the illustration because I'll do it live in a few minutes with GeoDa and GeoDa Space, but this is how it looks like. So the notion of model comparison, which is, again, a common source of confusion. And the reason why it is a source of confusion is because in so much of your standard statistics, the emphasis is put on R square as a notion of explained variance over total variance. So in the linear regression model, that is in fact what the R square is. It gives you a good sense of the share of the overall variability, the share of the overall variance that your model can capture, that your model can explain. So why does this not work in a spatial case? The basic notion underlying the R square is that each squared residual is of equal value. So sum of squared residuals, right? In the spatial case, this is no longer true because they're all interconnected. And the notion of spatially weighted regression is a notion that affects the weight of each residual, so to speak, in the overall objective function so that it reflects the correlation between these error terms. Just let me give this in a different context, heteroscedasticity. So heteroscedasticity means that the variance of the error term for each observation is different. So then, if you do weighted least squares for heteroscedasticity, what do? You downweigh the observations with a large error variance, and you give higher weight to the observations with a smaller variance. This is the same idea, except it's not simple downweighting and upweighting. It's much more complex because it takes into account the full covariance of these error terms. Right? And that's why you have this inverse matrix in the weighted least squares. It's no longer diagonal, it's a full matrix, but it still weighs an inverse proportion to the variability. So the less variability, the more weight, the more variability, the less weight. So the R square as being based on the unweighted sum of squared residuals doesn't compensate for what we know is basically a loss of information. So how do we deal with this? And there are a number of solutions. There are some very sophisticated solutions that were developed a long time ago where you basically use a form of weighted residuals, weighted square residuals to compute an alternative R square. But as far as I can tell, nobody uses that anymore. I have it in my 1988 book, but lately I haven't seen anybody use it, nor have I seen it mentioned in textbooks anymore. So in part probably because with larger data sets it doesn't really matter that much. But what we can use instead is something which is used a lot in models where this notion of explained variance doesn't really work, and that's a notion of a pseudo R square. And typically a pseudo R square is the correlation or squared correlation between observed and predicted. And of course, here again we get in trouble with the lag model. Which predicted value do we use? And so in the lag model, to get a pseudo R square, we really need to use the predicted value from the reduced form. Right? And it's an R square, it looks like an R square, but it's not a real R square, right? That's important to keep in mind. So it doesn't reflect this notion of explained variance proportion, but it is roughly true that a larger pseudo R square is better than a smaller pseudo R square. But what exactly these numbers mean is not directly related to explained variance. So if you have 0.5, you can't really say that you explain half of the variance. You explain something, but and 0.5 is better than 0.2, but these magnitudes are not directly comparable because they incorporate the full dependence, and that's a very complex interaction. So instead, what we can use is something which is not really a measure of fit, although it's often confused with a measure of fit. That's the notion of a maximized log likelihood. And you can think of this as, if you've done any optimization, as the value of your objective function. So if you do, say, linear programming and you want to find out the best allocation of resources, and one allocation gives you 100 for the objective function and another allocation gives you 200, 200 is better than 100. So you can think of it the same way in terms of comparing these log likelihoods. And because they all pertain to the same dependent variable, they're all in the same scale. So as long as they're within, how should I say this, comparing different alternative models for the same dependent variable, you can compare the log likelihood. But you cannot compare them between two different dependent variables because they're scale dependent. And you'll see, sometimes you get negative ones, sometimes you get positive ones. Sometimes these are huge numbers, sometimes these are tiny numbers. It depends on the scale of the dependent variable. So it's not really, strictly speaking, a measure of fit, but it does give you a measure of relative model adequacy. And typically these are negative. Not always. I've seen a few positive ones, but typically they should be negative. And you take the highest value is the best. So the smallest absolute value, because they're negative on the negative scale. So minus 10 is better than minus 20. Right. So that is a comparison of models. Now, similar to what we have with an R-square and an adjusted R-square, there is a danger of overfitting in that the pure R-square always goes up when you add more variables to your model, irrespective of whether the coefficients of these variables are significant or not. The R-square will always go up. The adjusted R-square, which is a correction for degrees of freedom, does not necessarily go up. Right? And so you have a same notion here, and this notion is called an information criterion. And there's a bunch of them, of these information criteria that are basically starting from the maximized log likelihood and then apply some kind of correction to them, which is typically a function of the number of parameters, sometimes also the number of observations, but there's a bunch of them out there. The one that I just want to highlight here is known as AIC, or the Akaike information criterion, and is a very easy one. It's minus twice the likelihood, minus twice the number of variables in the model, right? And because it's minus, the interpretation is the opposite of the likelihood. Whereas you want the highest likelihood, you want the smallest information criterion. And so you can have situations where the likelihood of one model is better than another model, but if you wish, the adjusted likelihood, the information criterion, is not. Say if one model has 5 variables and another model has 8, the one with 8 will always have a higher likelihood than the one with 5. But the question is how much higher, right? Is it worth it? And so just like an adjusted R-square penalizes you for adding more variables, the information criteria penalize you for the complexity of the model. So the idea is to have a simpler model, basically. Just like with the maximized likelihood, the magnitudes are not necessarily that meaningful, right? It's the relative values that really matters. So if you have, again, different models for the same dependent variable, you can compare the AIC, and you can take the model with the smallest AIC. Now the trouble with, it's not really trouble, but the issue with these spatial models is that they all tend to have the same number of parameters. And you're typically interested in comparing a lag model against an error model. And there the AIC and the likelihood will give you the same result because there's exactly the same number of parameters. One thing to watch out for is that in some software, you see, it's not clear what counts as a parameter or not. And some literature would argue that the parameters in the error term, like the spatial error autoregressive parameter, don't count for the information criterion. Others would argue that it does count. So if it doesn't count, then the lag model will always have one more parameter than the error model because you're not counting it. Just to give you an example, you typically don't count the sigma square as a parameter. You count the betas. So if you don't count sigma square, some would argue, why count lambda? Right? It's also part of the error term. So whether you do or not will affect the outcome of the AIC because your k will differ by 1. Right? So again, keep that in mind when you use software that you didn't write yourself. When you write it yourself, you know exactly which assumptions you made. Okay, so let's look at this, for example, and I'll get back to this in a few minutes. So this is a standard output in GeoDa for an error model, and we can look at the log likelihood, minus 4471, and then you see the likelihood is negative, the AIC is positive. So we take the largest, least negative likelihood, and we take the smallest AIC. So then that's why in GeoDa it gives you the likelihood, even though in OLS you don't need the likelihood. It's an additional assumption of normality which is not actually needed to get the OLS results. So there's the log likelihood in OLS. And then just for completeness, there's the log likelihood in the lag model. So now we have 3 log likelihoods and 3 AICs, and we can compare them. So you see the error model is the least negative, so the smallest in absolute value of the 3. So this would argue in this particular specification that the error model has the best quote-unquote fit, even though technically, strictly speaking, it's not about a fit. It's about the value of the objective function that we maximize, right? And, you know, as a lot of these models, it's not that clear-cut. So we might have to think about this model some more. It's just an example that I'm throwing out there. Okay, let me talk a little bit about computational issues, and then we'll switch to the software. So we already know the likelihood is strange, right? It's not your typical product of the probabilities for individual observations or the sum of the logs of the probabilities for individual observations. You have to model the joint distribution. So everything is about multivariate normal. And just stepping back, to tie back into something we discussed a couple of weeks ago, remember when I talked about how only for a normal distribution do we keep the same distribution for marginal, conditional, and joint distribution. So if we say the marginal distribution is normal, then the joint distribution is multivariate normal, right? If we have a model for counts, and we say the marginal distribution is Poisson, and we don't have independence. If we have independence, no big deal. Just add up all the logs of the probabilities. But if we don't have independence, then we can't do that. Then we have to figure out what is the multivariate counterpart of this. And it's not Poisson. It's complicated. You can do it for 2 variables. You can actually do it analytically, but for more and in general, it becomes very, very complicated. So that's a problem with applying maximum likelihood to a model with count variables that shows spatial dependence. And that's why, you know, I mean, in part because it's the only thing that works. The approach taken in the literature is an indirect approach in a hierarchical specification with a random effect specification, where you don't model the dependence of the dependent variable directly, so of the counts, directly in some kind of multivariate counterpart of this Poisson distribution, but we model the dependence through dependence of the parameter, which becomes a randomly varying parameter that has a component that is spatially correlated. So it's kind of a backdoor way to get the spatial dependence in the counts. You get them by building spatial dependence in the parameters of the count model that then determines how many counts you have. So it's a two indirect approach. So that's the one thing. We need to take care of this dependence. The other thing is the presence of the Jacobian term, which is computationally a beast, right? It's the, I mean, I don't know how much computational work you've done, but if you work with matrices, you know that once they get really big, things don't work that well. And the problem is computers, you know, sometimes they blow up, sometimes they crash, but oftentimes they give you results, but the results are meaningless. And that's the danger in scaling up these approaches. So we have a number of large matrix expressions that are very complicated. The log Jacobian, in the first order conditions, remember my complicated traces with an inverse of a matrix. In the variance terms, we have complex expressions that are, this is a product, the trace of a product of 4 matrices that are of dimension n by n. Now W and W prime are very sparse, mostly 0. But these inverses are not. They are dense. And so that creates all kinds of complications. So how do we deal with this? One early solution that seemed very tractable, except that there's a catch, is that you can write the determinant, and if you remember some of your linear algebra, you will see this. You can write it, I mean, the determinant of a matrix is the product of the eigenvalues of the matrix. That's a standard result. So if we could figure out what the eigenvalues were of this matrix, we'd be in business. And as it turns out, the eigenvalues take on a very simple form of 1 minus the parameter times the individual eigenvalues. So the product of this expression, 1 minus rho omega I, where omega I has the eigenvalues, is actually the determinant. So then the log of this is simply the sum of these terms. And that's really easy because rather than having to compute a determinant each time, we get the eigenvalues and then we just have to do a sum of the logs or a product of the terms. So that's great, except have you ever computed eigenvalues of a matrix? I mean, you just push a button, then they come out, right? But that's not a simple thing to do, especially when the matrix is very large. And for all practical purposes, as soon as you hit a couple of thousand to, depending on the machine precision, 10,000, but basically not much further than that, you get garbage. Because the way these are computed is by pivoting rows and columns in the matrix, and every time you pivot, you multiply. So as you keep multiplying, and you should do this once in a computer, if you multiply zeros together long enough, you get something that is not 0. Now, you know, in a textbook this never happens, of course, right? But computers are only approximate. They cannot deal with 0 doesn't exist. You've got to store it somehow in there with a certain degree of precision. And as you multiply, there's overflow issues, and that creates non-zero out of 0. And of course, the computer doesn't know this and treats these numbers as if they're real, and that's how you get results, but the results are garbage. So anything with eigenvalues, I take with a big grain of salt because it doesn't scale, right? Theoretically, very attractive, very elegant solution. As long as we were in a small data world, you know, Ord, his example was for 26 observations. So, piece of cake. You know, you can maybe even do it by hand if you have a lot of time. But this day and age, you know, if you scale up to hundreds of thousands and millions of data points, forget it. Eigenvalues are out. So then, I mentioned this. There's all kinds of tricks to trying to save your life. If, you know, it's really complicated to do eigenvalues of asymmetric matrices. So a row standardized weight matrix is not symmetric. Even though, I mean, this is linear algebra, right? The eigenvalues of a symmetric matrix are all real. The eigenvalues of a general asymmetric matrix may be complex numbers. Remember those things with a funny little I in them? Those are complex numbers. Now, because this is a Jacobian, it can't be a complex number. It has to be a real number. And it is, and you can show this. But you only get to the real number by multiplying a whole bunch of complex numbers, such that the complexity cancels out. And that's another complication that you have to keep in mind. And so it keeps on going on and on and on. And there's a whole literature of dealing with this, of approximating the Jacobian, of simulating the Jacobian, and I've done some work on this as well. It's a lot of fun. The algorithm that we have in GeoDa is based on a characteristic polynomial, and it scales really well, although it's totally dependent on the sparsity of the weights matrix. So if you have a very sparse weights matrix, this scales up to 1 million. If you have a dense matrix, forget it. It crawls to a halt, okay? So that's what I wanted to do in terms of the let's see, I want to make sure my recording is still going. It's still going, yeah. So I'm going to live dangerously here and start the safe version of GeoDa. And I say this because, as Julia knows, I am living dangerously, and if you check out the GitHub site of GeoDa, you can see what I mean by that. But anyway, we're going to keep it simple, and we're going to work with the NAT regimes data set, which is the county data set, with the homicide data. So the variables in here are some identifiers. We saw that Phipps number is the identifier for the counties that we need, and here are some homicide rates for 60, 70, 80, 90, and then a bunch of other explanatory variables, resource deprivation, a population component variable, unemployment rate, divorce rate, some things like that, right? Classic sociological model. We want to make sure we have a weights matrix. We are going to load one because I already did this ahead of time. And by now you should know how to do this because you're going to need it for your paper. So now we have the weights matrix. So we won't do anything in terms of exploration. That's not necessary. We go straight to the regression interface. So that's this button here, or you can go in the menu and click on regression. This is kind of a silly menu because it only has one thing in it. But that's the interface, right? And the interface is, you know, rudimentary. You pick your variables and you put them in the boxes. So in GeoDa, there are only two boxes. One for dependent variable, and then one for the explanatory variables. In GeoDa, there is no allowance for endogeneity. So if you want endogenous variables on the right-hand side, you can't use maximum likelihood. GeoDa only has maximum likelihood. So as I mentioned, GeoDa implements this characteristic polynomial algorithm for data sets. I forgot what the cutoff is, but once they're over a certain size, it switches to that algorithm. And that algorithm only works for weights that are intrinsically symmetric. And let me clarify what that means. So if we have a contiguity weights, contiguity is a symmetric concept, right? If county A is contiguous to county B, then county B is contiguous to county A, right? So that's an intrinsically symmetric weights matrix. After we row standardize it, it's no longer symmetric in a strict sense. But for the algorithm, that doesn't matter, right? So contiguity, distance bands, all fine. In contrast, if you have k nearest neighbors, that is not a symmetric property. So if B is, say, the third nearest neighbor to A, that doesn't mean that A is the third nearest neighbor to B. There may be other neighbors on the other side of B that are closer than A, right? So a k nearest neighbor weights matrix is not intrinsically symmetric. So that's another limitation of the routines in GeoDa. You cannot use k and n as the weights. And in the old days, it used to crash, or it would give you nonsensical results. I think now it gives you a warning, but I haven't tested it in a few days, so I'm not sure. But basically, don't do it. So if you're going to do maximum likelihood for the spatial models in GeoDa, use either contiguity weights or distance band weights. If you want to do k and n, then use the non-maximum likelihood methods that we'll see 2 weeks from now. So next week we'll deal with diagnostics, and then we switch to GMM as the estimation method, and then the last 3-ish lectures will be panel data. Right? So let's take homicide rates in 60 as a dependent variable. You can either double click or click on the little arrow, and so you see it ends up in the box for the dependent variables. Right? And then we go down the list and start picking out our explanatory variables. So we take RD60, PS60, UE60, DV60, and MA60. And I always forget what exactly these are, but the book explains it, and the data set is also on the Spatial Use Chicago sample data sets with the metadata and everything you want to know about it. I use it a lot because it is a nice kind of manageable data set. 3,000 still works for the eigenvalues, marginally. And it has different time periods, so I can use the same data set for pure cross-section as well as for panel data illustrations. And it illustrates, I should say, the case in panel data that I'm most interested in, which is the one with a large n and a short t. As we'll see later, there's all kinds of different combinations, small n, large t, equal size n and t, and all these different combinations. But from a spatial perspective, the most interesting case is large n and small t. So we have 4 years. We'll just do 1 year here. Next thing you have to do is specify the weights file. And if you loaded or created a weights file, it will be in this list here. If you have multiple weights, you can use this little arrow here to pick out a different weights file. If you forgot to create one, you can create it with this little W, and it will be there, right? So that's all pretty straightforward. And then here are the choice of the different models. So the classic model is just standard OLS, and let me just run it. And that's just a standard regression model with the diagnostics that we'll talk about next week. So I'll just put this here kind of for reference so you see what the coefficients are, and you see the log likelihood for that particular model is here. And then next week we can compare them. So then there's a couple of things you can do. I won't do them, but you can save the residuals and the predicted values to the data table. So if you want to, for example, make a map of predicted values or a map of residuals, this is how you do it. You can also save these things to a file, and if you reset, then you clear this whole thing out. Otherwise, it stays there, so you can do standard regression, lag, and error all with the same specification. Actually, as I said earlier on, this is just click, click, click. There's really nothing to it, right? So you take the second radio button and you press run, and you have the spatial lag model. And I do want you to appreciate how fast this is, right? If you've used other software, you might appreciate this. If you've never used any other software, then of course you wouldn't know. But this is, I think, still the fastest thing out there to estimate a spatial lag model. So what's different about this? Really nothing, except that we have WHR60 in there as an additional parameter. That's the spatial autoregressive parameter. The standard error is computed from this really complicated asymptotic variance covariance matrix. As I said, the reason I like this data set, it's not 26 observations, but it's still in the range where the inverses and the determinants can be computed relatively quickly. So it's not prohibitive in that sense, but we're definitely getting there. We're getting to the border. Now, what's happening in part is that our processors are getting better, I mean, most processors we have now are 64-bit. They used to be 16-bit. There's a big difference in terms of the precision that you can carry, and that has to do with rounding errors. So since rounding errors is what kills you in these approaches, the more bits you carry in your processor, the least sensitive you are to these rounding errors. So as we get better and better CPUs and processing facilities and ways to deal with memory, we can push these boundaries out a bit, but they're still there. They don't go away. There is always a point where your results become gibberish, basically. So other than that, we have the test we'll talk about next week, and we can look at the results in comparison. I think, just kind of barely pull them all on the same screen. So you see the effect on the parameters. They tend to, and that tends to be the case, they all tend to be a little bit smaller in absolute value. So if you think about it, what's going on here? So when you don't have the spatial lag term in there, the other parameters pick up the interaction effect, right? And now that we introduce the spatial lag term, in some sense, we're filtering out that interaction effect and take it out of the actual estimates. And now with these estimates in hand, GeoDa doesn't do this yet, maybe someday I'll do it. You can figure out what are the direct effects. Well, the direct effects, you can just see them, but what are the indirect effects and the total effects? And you get those by combining the betas with the estimate of the rho, to look at the spatial multiplier effects. So then the error model, we click this, we say run, and it's done. And here the only thing that changes is that we get this lambda estimate with a standard error, and everything is highly significant. As I mentioned in the example in the slides, the log likelihood is negative, the AIC is positive. If we put them next to each other, we see here, so let's take the AIC, for example. We want the smallest one, right? So we have 18,338. We have 18,300, which is better. And then we have 18,490. So that's the worst. So OLS is the worst, and the other two are better than OLS, but of the two, the lag model is a little bit better in this particular case, right? If we look at the log likelihood, it's the other way. It's not the other way around, but it's an opposite sign. So we're looking for the smallest value in absolute value here. So 9163, 9143, which is also better again, and here 9239. So that's the worst one, right? So that's, in a nutshell, what the spatial lag and error models do in GeoDa. So it's, you know, really easy to do, right? You don't have to know anything. You just click on the buttons and it runs. Okay. So let's get out of GeoDa, and then I'll show you GeoDa Space. I think I mentioned earlier that as of, you know, what we call internally GeoDa 2.0, all of GeoDa Space will be inside GeoDa. So it just will be one piece of software that will do all this stuff. So GeoDa Space looks very similar because it is basically using the same GUI tools, but it's a little bit different in that it's not as integrated with the exploratory facility. So it's kind of on its own. And the first thing we have to do is load a data set. And GeoDa Space, unlike GeoDa, which reads just about any format, GeoDa Space only reads DBase, DBF files, and comma-separated text files, CSV files. And so we bring in a file with this little icon here, open data file, and I'm going to my desktop lab. So I'm going to pull in the NAT regimes DBF file. So as I open this, then you will see a new window opening that lists all the different variables. So here they are. And GeoDa Space, in contrast to GeoDa, has many more boxes, right? For now, we won't use them all because, as I mentioned before, the maximum likelihood estimation doesn't allow for endogeneity, so we don't need instruments. So this box, YE, is for endogenous variables, and instruments is for their instruments. R is for regimes, which we talked about in the heterogeneity. T doesn't work yet. And then in terms of the weights, we have model weights, which is what we're going to use here, and then kernel weights, which is for the hack estimation, which we'll talk about that later. So to get your model specified, you pull a variable from this list and you drop it in the box. And you can use a search filter, but I never do that. Because I know where they are. So we pull HR60 into the Y box, and then we go down the list, just like we did before. We take RD60, we take PS60, we take UE60, DV60, and MA60. So I forgot to mention, you know, when you have the output listed in GeoDa, you can save that to a file, to a text file. So it doesn't go away. So this is our basic specification, and then we need a weights file, which is going to be our NAT regimes Q file. Here, this one. This is a Queen contiguity file, and we open it. So now we have all the pieces that we need. Down here is the model type. Let's start with the standard model. We take OLS, and in contrast to GeoDa, you can do heteroscedastic consistent standard errors, the white or sandwich standard errors, which just to show you, I'll flag this. So then we run this, and again, this is instantaneous. So what you get is actually two regression results. The first one is the standard OLS result. Again, this is all the exact same format as in GeoDa. They're all using the exact same format. The different diagnostics that we'll talk about next week. And then in the bottom is the white results. You see it here, it says white standard errors. And if you look at the tables carefully, I know the numbers are kind of small, but I can make them bigger actually. So the estimates in these two tables are exactly the same. Oh, I got to go a little bit smaller. Here. So you see 10.516, 10.516, 1.295 is the same. The standard errors are different. So here you see 0.61, 0.65, 0.09, 0.11, 0.019, 0.020. It's basically the same. So that's the effect of correcting for the presence of heteroscedasticity of unknown form. So in most cross-sectional situations, that's best practice. Because as, well, we've seen, a couple of weeks ago, the standard diagnostics for heteroscedasticity, like Breusch-Pagan, the White test. If you paid attention, all of these are hugely significant in these models. So heteroscedasticity is the rule rather than the exception. In fact, even standard econometrics textbooks will tell you that whenever you work in a cross-sectional situation, you should take into account heteroscedasticity. Okay, so now we move on and we switch to the lag model. And as I said, this is mostly here for illustrative purposes. You see it automatically jumps to GMM as the estimation method, which is the preferred approach. But since we're doing maximum likelihood here, we'll do ML. And if you paid attention, you'll see that the checkbox in white is gone because there is no white standard error for maximum likelihood. Maximum likelihood standard errors are based on the asymptotic variance matrix. Then I want to show you some other things. Up here in this kind of wheelie thing gives you a bunch of preferences for GeoDa space. And the ones that we're interested in are the ones under the ML, the maximum likelihood button. And particularly these methods. And so you see here, there's two methods implemented in GeoDa space. Actually in PyCell, if you like command line, there is one more. It's called LU for LU decomposition of the matrix. But this is, mostly for illustrative purposes. So it's the full brute force method, which means we actually compute the determinant as is every time, or the ORed eigenvalue method, right? So in GeoDa, neither of these are used. GeoDa uses the characteristic value approach. So let's just keep it at full and keep our fingers crossed that it will actually work. I honestly don't remember, but I think it does. Say that 10 times. Yeah. Why does it test?
No, like all the statistics that we're seeing, they are proving for if they are finding heteroscedasticity or not.
Yeah, the heteroscedasticity, the reason that these diagnostics are there is that heteroscedasticity is very common in cross-sectional data, especially when you have areal units that are not the same size. So basically, heteroscedasticity says that your model does not have the same precision everywhere. And in microeconometrics, for example, that's a standard assumption. You do models based on surveys of people about their employment or education or anything like that, it's really difficult to assume that the precision of that model will fit each person equally well. So now that we have the white sandwich estimator, you know, you basically won't get away with not doing that if you do an empirical exercise on cross-sectional data or individual microdata, you know. So that's why it's built in and given in any one of these. We'll talk about the spatial diagnostics next week. So they're here, but I'm not saying anything, right? So you see that it did actually, if I mean, I can't tell. Yeah, it did work. It's at the bottom here. So let's make it a little bit larger. So we see that, you know, I know that you all have a total visual memory and can remember these coefficients that we just saw in GeoDa. Well, they're the same, right? The differences appear, you know, in the 6th decimal or something like that. So this is the lag model, and then the error model uses the same approach. So brute force again. So it's going to take a few not a few minutes, but, you know, a few seconds. But you see how much longer this is than the GeoDa one, which was instantaneous. You know. There it is. Yeah. So it's still not, I mean, you're not going to sit here for 20 minutes, which I'm afraid to say you might do in other software packages. But still, I mean, this is fairly fast. It gives you lambda. It gives you the likelihood. It gives you the Akaike criterion. So it's exactly the same as in GeoDa. There is no advantage to using GeoDa Space for maximum likelihood relative to GeoDa. In fact, you have every advantage in GeoDa as long as your weights are intrinsically symmetric, right? Since this uses brute force, it will work with KNN, but it will take longer, right? The preferred approach, when you have heteroscedasticity, is to use, and definitely when you have endogeneity, is to use instrumental variables and GMM methods. The reason I cover maximum likelihood first is just to give you a framework. It's an estimation and testing framework, because everything we'll talk about next week, you know, Wald test, likelihood ratio test, Lagrange multiplier test, is based on this maximum likelihood framework. So in the past, sometimes I do the diagnostics first and then the likelihood later. Sometimes I don't even talk about maximum likelihood, although it's in every textbook, because in practice, and I will say this again 2 weeks from now, the preferred approach is not to use maximum likelihood for 2 big reasons. One is that, especially in applied economics, it's very difficult to maintain that all the variables on the right-hand side are actually exogenous. I mean, I know it's the easy assumption, but it's often, for example, here, and I mentioned this before, when you deal with crime, unemployment rate is really not exogenous, because you can flip it around. You can have an equation for unemployment rate and have crime on the right-hand side. So whenever you can do that, then you know that one of these is endogenous. So then you need instruments. You can't do that in maximum likelihood. I mean, you can spell out a full model with all the endogeneity in it, full information maximum likelihood, but at this day and age, almost nobody does that anymore, right? It's not necessary. So the other reason is heteroscedasticity, is that it's prevalent, and that's why, you know, it's reported. It's all the time you run into this. So here we're using a method that basically ignores that. And how serious is that? Well, we'll see later. But it can be serious in that you lose the consistency of your estimator in some circumstances. Because remember, there's all these assumptions that you make, Basically, maximum likelihood is great as long as all your assumptions hold. But if your distribution is not normal, or if your variance is not constant, then you have to take that into account in the likelihood function. And if you don't do that, then you're still maximizing a likelihood function, but it could be the wrong likelihood function, right? So let's leave it at that for today, and then next week we'll move on to diagnostics.